this 16 is moved to C errors. After completion of this task 2, RTOS switches to task 1. Now it continues from where it was interrupted. Here C new errors was calculated, but before that was stored to C errors, task 2 was scheduled. Now when the RTOS switches, so instead of showing the total result, total number of errors, that is C errors as equal to 25, now R1, the C errors shows the earlier R1 value, that is 14. This is what happens, but this shouldn't have happened, right? So this is all because of shared data problem. Now we look into the previous example. So the same problem arises in this program also. Here RTOS might stop calculating the level task as soon as a high priority button task arrives, and here this is in a non-atomic way. We have seen about the atomic operation in the previous unit. So here the V respond button might read only the half changed data. Next is semaphores and share data. We'll see how semaphores can be used to avoid share data problem that we have seen previously. Semaphores are Semaphores are the tools that are mainly used to avoid share data. This is an example wherein in olden days railroad barons discovered that it was bad for business if their trains ran into one another. One solution was to use signal mechanism called semaphores. Here, any train before entering into this junction or before going into the next junction, it should check this signal pole. If this is raised, that means the train can safely enter into this zone. Here, if uh, signal is not raised, that means another train could be there within this junction and the train has to wait till the signal is lifted upwards. In the same way, here we are using semaphore to check this share data problem. So this is how we are going to use the semaphores to protect the data. This is the button task, that is the high priority task. So this is blocked until the user pushes a button. And before getting into this data of time and levels, we need to take a semaphore. Only if take semaphore is successful, the RTOS can enter into this section, and after completing this part, it is going to release the semaphore. Same. So this is the level task. Here also, before calculating the tank level and time, updating the time, it has to take the semaphore. Only if the semaphore is free, the RTOS can enter into this section and it needs to release the semaphore. We'll look into the execution flow with semaphores. To start with, the low priority level task will be calculating the tank levels, that is, and before updating the time, it needs to take a semaphore. Takes the semaphore, time is going to be updated. And before getting into the next instruction, suppose the user pushes a button, the high priority task button task unblocks and the RTOS switches to that high priority task. Now it is going to take the semaphore, but that semaphore is already taken by the low priority one. So this task again goes, high priority button task goes into blocked state and it switches back to low priority one so that it can release that semaphore and that semaphore can be taken down by the high priority task. So this is the low priority task tank level. It completes its task, releases the semaphore, and now this high priority button task, now after releasing the semaphore, unblocks the button task and the RTOS switches again. This high priority task is going to complete its task and the button task once again gets blocked until the user presses the button and the RTOS resumes the level task, that is the low priority one. Next is the semaphore problems. There are a different number of ways in which we can mess up while using the semaphores. One is before getting into the critical section code, we might forget to take the semaphore itself, wherein we are really going to mess up with the data, or forgetting to release the semaphore once we have taken the data, once we have taken the semaphore, so that that task will be blocked forever, because none of the other tasks can get into it. Next, taking a wrong semaphore which was not pertaining to that specific task, or holding a semaphore for too long, that is, it makes the other task to wait until the semaphore is released. So many of the tasks might miss real time deadlines. Now we shall see that with an example. Here task C is of low priority, task B is of medium priority, and task A is of high priority. So let us assume that task C has taken the semaphore, and it shares the same data with the task A. Now here, after completion of while executing the task C, task B arrives, which is of higher priority when compared to this task C. So task B gets a message in its queue and it unblocks. Now task B is under execution. After some time, task A gets a message and it unblocks. Since this is of highest priority, RTOS switches to this task. Task A now tries to take the semaphore that has already taken by this task C. But it cannot directly go to this task C, and this gets blocked. Now, task B is taking a very long time to complete its execution. Thereby, task B goes on running and running and running, but never giving task C a chance to release the semaphore. If a chance is given to task C, it can complete its task and release the semaphore which it has taken. And for the same semaphore, even task A is waiting. And since this task B is taking a very long time for execution, task A, which is, even though it is of higher priority, because of the unavailability of the resources, it is going to be blocked. And this problem is called priority inversion. And some RTOS resolve this problem by priority inheritance. That means they are going to temporarily boost the priority of the task C to that of task A whenever task C holds the semaphore and task A is waiting for it. That means this task C is going to be assigned a high priority so that task C can complete its execution and release the semaphore, and task A can acquire that semaphore and complete its task. This same thing is illustrated with an example. So an illustration of the problem called deadly embrace, how exactly it operates. This is an example how a deadly embrace happens, or the share data problem happens in case of RTOS. Here it's an RTOS named AMX, which is going to hold two semaphores A and B. Here the task 1 is, these are the two functions, AGSMRSV is reserve semaphore, and these two functions are to release the RLS is release, RSV is reserve. So this task wants two semaphores, semaphore A, semaphore B, and these two are other additional parameters like timeout or priority information, and that are not much relevant here. Now reserve the semaphore A and B, then perform some operation A is equal to B, and then after performing the operation release both the semaphores B and A. Task 2 also wants to reserve the semaphores B and A, perform some operation, and then release both the semaphores. Now task 1 acquires semaphore A. By the time it gets into the second instruction of reserving the second semaphore, task 2 gets into the processor. That means task 2 is assigned the CPU time, and this acquires the semaphore B. Since it was free, it was not acquired, it acquires semaphore B and tries to acquire semaphore A. But when it tries to acquire the semaphore A, it cannot, because the semaphore A is already held by task 1. Task 2 also cannot move ahead because it is waiting for the task 1 to release semaphore A. Similarly, task 1 is also waiting for the semaphore B, which is held by task 2. This kind of uh, problem, we call it as deadly embrace, wherein none of the tasks are able to move ahead. Different variants in semaphore. One is the counting semaphore, then resource semaphore, and the mutex semaphore. Then we have seen the different ways to protect the share data. One is via disabling interrupts, another one is by taking the semaphore, and the last one is disabling task switches.